Welcome to module 2.5 and we will be constructing an ALU using whatever we have seen so far. We have seen multiplexers, we have seen demultiplexers, we have seen 4-way multiplexer, 4-way demultiplexer, 4-way n-bit demultiplexer, 4-way n-bit multiplexer. So many varieties that you have seen. I hope you have coded all those things in your project 01. Now we will use that to basically construct this ALU as a part of this particular module. I will basically define what the ALU is, and then we will go ahead and basically construct the ALU. So the ALU is a hierarchical design which will use all those components you have done in the previous project, that will be used, that will be instantiated, and you construct the ALU out of it. So ALU is nothing but taking all those components and connecting them together. So you will realize that how easy it is to build this ALU, provided you have got the basic building blocks. This is typically how a normal even a billion transistor mobile chip is made, wherein there are certain building blocks that are already available. People will take those, the designers take the building block, connect them together to make a large chip. The same thing is what we are going to see here, but in a smaller way. We will be constructing a small 16-bit ALU. So I will now define the ALU for all. So there are two inputs, I call them X and Y. These are basically 16 bits each. That is why we call it as a 16 bits ALU. Right, and so these X and Y basically are the data inputs to the ALU. And the ALU will output again a 16-bit answer, which will be some function of x comma y. What is that function? Some other inputs will determine what is this function f, right. This is the data output of the ALU. So the ALU, when you view an ALU, you view it in two parts. One is the data part, another is the control part. The data part will tell you how the data comes in and what is the path of it to go out. The control part will tell you what will the ALU do with the data. The F here is basically determined by the control part of the ALU. So this is the data input and this is the data output. What are the control inputs? So there are, in this ALU there are 6 control inputs, namely Zx, Nx, Zy, Ny, F and N0. And there are 2 outputs which are Zr and Ng. Now what will, so when Zx is 1, right, then whatever be your input x, that x will be reset to 0. So you can give any input x, you can say x is 16 bit, right, you can give some value on that 16 bit, some 1100 whatever. But the moment I make Zx is 1, x will become 0. So whatever you send inside will not go in, only 0 will go for x, right. Similarly, when I make Nx is equal to 1, whatever input you give to x, it will get inverted. So if I give say 1 0 0 1 1 1 0 1 1 1 1 1 0 0 1 0, 16 bits for x, this will become 0 1 1 0 0 0 1 0 0 0 0 0 1 1 0 1. So, it will just get inverted if the nx is 1. If the zx is 1, all these things will become 0. Right. But if both zx and nx both are zeros, right, zx is equal to 0, nx is equal to 0, x will go as it is here. But the moment I make zx is equal to 1, all these inputs will be converted to 0. When I make nx is equal to 1, all these input will get inverted. Similarly, for zy. So, this is for zx comma nx. The same thing is true for zy comma ny, as you see here. This is zx nx, this is zy ny. Right. Then what is f? When f is 1, then x plus y is calculated. If f equal to 0, then x and y is calculated. So, when f is equal to 1, out will be x plus y. When f equal to 0, out will be x and y. So, that is how f is defined. And what is NO? NO is after you compute the output, if NO equal to 1, after you compute this f of x comma y, whether it is x plus y or x and y, you invert it. So, the normal output will get inverted when NO equal to 1. When NO equal to 0, the output will come as it is. So, this is how those 6 control lines will behave. Right. So, the 6 control lines will tell what you have to do with x and y before you send them as output. Right. And then there are two more outputs here, namely ZR and NG. ZR will become 1 if output is 0. NG will become 1 if output is less than 0. So, by looking at ZR and NG, you can find whether the output is 0 or the output is less than 0 or the output is greater than 0. When both are 0, when ZR is 0, that means NG is not 0 or output is not 0. When NG is also 0, that means output is not less than 0. So, when the ZR and NG both are zeros, we know that the output is greater than 0. So we can quickly, as I had seen in 2's complement arithmetic, we can very quickly find out whether an output is a negative number or a positive number. Depending on that, we can set up this ZR and NG. Right. So, this is how this entire ALU basically works. Okay. So, now we will discuss a bit more about the ALU and tell you how we can use that ALU for different types of operations. So, let me just redraw this ALU for you. This is the 16-bit ALU and I have the x and y, the data coming in 16 bits, and then this is output which is 16 bits, and then I have ZX, NX, ZY, NY, F, NO, those 6 control inputs that we had discussed in the previous slide, and then of course we have this ZR and 0 and not greater than NG. Right. So, we had basically seen, so let us just go about, suppose I say let us now just draw something like ZX, NX, ZY, NY, F, N0. Suppose I make 1 0 1 0 1 0, what will be the output? Since ZX is 1, your x becomes 0, NX is 0, your x does not get inverted, x is 0 means all the 16 bits are zeros. Since ZY is 1, this also becomes 0, all the 16 bits become 0. irrespective of whatever you are sending on this x and y here. If z y is 1, y becomes 0, and f is 1, f is 1 means you add. So, x plus y will again give me 0, NO is 0, this output whatever is generated is not going to change. So, the final output would be 0. Suppose I put 1, 1, 1, 1, 1, 1, what will happen? Now, x, since zx is 0, x is 0. Since zy, since nx is 1, this gets inverted. Zy is 1, so y becomes actually 0. Then since ny is 0, ny is 1, I am looking at the second here, ny is 1, this also gets inverted. So, your y again becomes 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. Now, when since f is 1, that means I add. So, I add 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 with the same number. So, this 1 plus 1 is 0, there will be a carry 1 above, 1 plus 1 plus 1 is 1, again one more carry here, 1 plus 1 plus 1 is 1. So, this goes on like this, and then there will be one carry coming out of this, which is gone because the ALU can handle only 16 bits, that extra carry goes off. So, basically you will get 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 0. Now, since NO is 1, this output now, since f is 1 we added, now NO is 1, this output is now inverted. So, this will now become, because NO is 1, it will now become 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 1. So, what is the output? Output is 1, right. So, right. So, like that we can see some very interesting examples. So, let us say for example, I want to increment x, x plus 1. So, let us take this. So, this will be 0 1 1 1 1 1. Okay. I want to increment x. So, since zx is 0, x will come as it is. So, x will be that x 15, x 14 till x naught, x 1, x naught. And since nx is 1, this will become x 15 bar, x 14 bar till x 1 bar, x naught bar. Okay. Since zy is 1, y is 0 0 0 0. So, since ny is 1, it gets inverted. So, this will become 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1. So, what will happen finally, that since f is 1, we add this, f is 1, we add x 15 bar, x 14 bar till x naught bar, we add it with 1 1 1 1. Okay. And we get some answer, and this answer, so let me say this is O15, O14 to O0, this again we invert, right, because NO is equal to 1 here, we invert. So, this will become O15 bar, O14 bar till O0 bar. Our claim is that this will result in x plus 1. How? Let us take first x comes as it, when I invert x, what is inversion of x? Suppose I have x, yesterday in the previous module we saw, right, x plus x complement is nothing but 2 power n minus 1. So, when I say x complement, this is nothing but 2 power n minus 1 minus x, okay, right. To this I am adding 1 1 1 1 1 1 1. What is 1 1 1 1 1 1 1 1? This is nothing but 2 power n minus 1. So, to this x complement I am adding 2 power n minus 1, which is nothing but 2 power n minus 1 plus 2 power n minus 1 minus x. Again I am whatever answer I am going to get out of this x complement plus 2 power n minus 1, that again I am inverting. So, when I invert this, again I will get 2 power n minus 1 minus of 2 power n minus 1 plus 2 power n minus 1 minus x. So, essentially this becomes 2 power n minus 1 plus minus 2 power n minus 1 plus 2 power n plus x plus 1, right. So, this is minus. So, plus 2 power n plus x plus 1. So, these two gets cancelled. Yeah. So, finally, we have 2 power n plus x plus 1. What is 2 power n? So, 2 power n is this bit number 16, that is A16. So, we have from A0 to, so this is a 16 bit architecture. So, we have, so any number n will be n0, n1 to n15, right. 2 power 16 will be here, is a 1 here with zeros all. So, this 1 automatically will escape, because the computer cannot, our computers can only store up to 16 bits. This 2 power 16 will be a 17th bit. We start with A0, we go till A15, the 2 power 16 will be the 17th bit, right. So, this 2 power n, so n has been 16 here, right. So, 2 power 16 plus x plus 1 will essentially become x plus 1. So, that is how I increment x. Suppose I want to increment x, put x here, put zx 0, nx 1, zy 1, ny 1, f 1 and n0 1, the answer would be x plus 1, right. So, in this entire calculation, wherever we have used n here, this n is 16. This is true for any n bit architecture, it can be 32 bit, 17 bit, whatever, but it is also true for 16 bit. So, this is how we generate x plus 1, right. So, I leave it as an very simple exercise for all of you. So, you can refer to the book, your reference book, in page number 37, it is available in the reference book, but then we need to generate these functions. F of xi is equal to 0, f of xy is equal to 1, we have done these two. Then I want you to generate minus 1, x, y, not x, not y, minus x, minus y, x plus 1, which we have done. Similarly, y plus 1, x minus 1, y minus 1, normal x plus y, x minus y, y minus x, x bitwise and y, x bitwise or y. What is bitwise and is, as I mentioned, 0 0 0 0 is a 4 bit number, 1 1 1 1 is another number, bitwise, or let me say to make it a little more, 0 0 1 1. Bitwise and is 1 and 1 is 1, 1 and 1 is 1, 0 0. So, the bitwise and of these two is 0 0 1 1, or suppose I make the bitwise and of these two now can essentially become 0 0 0 1. Okay. Similarly, bitwise r, the bitwise r of this 1 r 1 is 1, 1 r 0 is 1, 1 1 1 1. This is bitwise r. This is bitwise and. Okay. So, this is bitwise r, as you see here I am putting a tick here. this is bitwise r. So, we need to realize this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 different functions we need to realize by giving x and y and by adjusting the value of zx, nx, zy, ny, f and no. By changing these values, you can basically realize these functions. So, you need to form a table where what would be the combination of zx, nx, zy, ny, f and no, those 6 control inputs. So, that the function that we are realizing would be these. For each one there is a combination there, that combination you need to arrive, so that you get this answer. We have already seen 3 such combinations. So, you have another 15 more to work out, and that is how this whole thing does. Okay. Now this is the module that we have finished. So, the project that we are supposed to take, just look at this. Now, this is the ALU. So, there is a full adder that we need to do as a part of this project. There is an half adder that we need to do. There is an 16-bit adder that we need to do. So, yesterday we talked about half adder, we talked about a full adder, and also we talked about a 16-bit adder, and right. And there is also a need for doing 16-bit incrementing, right. So, this is an increment of 16-bit. So, in should be incremented by 1, right. So, this you can use actually a full adder to increment this by 1, right. There can be some other little more intelligent way of doing this also, if we can try and do that, but nevertheless just use a full 16-bit full adder, 16-bit adder to do this increment. So, we are doing 4 components here as a part of your project 2, the adder, the first the half adder, then the full adder, then the actual 16-bit adder, then an incrementer. So, this is a complete hierarchical design. The half adder will use the full adder, the full adder will use the half adder, the 16-bit adder will use the full adder, and then the incrementer can also use the 16-bit adder. So, once you make this, then we need to make this ALU. So, this is the thing. So, the type of functions that we need are given here. So, I need to get x plus y, x minus y, y minus x, 0, 1 minus 1, x, y minus x minus y, and all these things we need to realize, right. So, we have realized 3 such functions, but there are 15 more such functions that you need to realize. The table for this is available in the book at page number 37. So, if you have the book, you can refer to that book, otherwise you have to think and get out with this. Some of them are not quite immediately doable, but you have to think to get these functions in place, right. We have done, for example, we have done x plus 1, it is actually not very trivial, but we did then show how x plus 1 works. So, like that we need to do for these functions here, and these functions are listed in your project 2, this ALU.html file. So, then we do, so the moment you finish an half adder, you populate this STL here, you put your code here, immediately you can go and load the script here, .txt script here, and there is already a compare script. So, it will say whether it is passing, whether your design is correct or not. Similarly, then with that you can build a full adder, again you can do this comparison. There is a compare and a test, there is a script for testing the full adder, then there is a script for testing your add 16, there is a script for testing your incrementer, there is also a test for testing your ALU. So, you can keep building. So, another small point is when you are constructing the ALU, so basically for you to realize these functions, all these functions could be realized just using the incrementer, the adder, the full adder, and the muxes, demuxes, multi-bit gates and other things that we have already constructed as a part of your project 01 and till now project 02. So, we have constructed lot of building blocks in project 01 and now we are we have constructed these 4 circuits, namely full adder, incrementer, half adder and half adder, full adder, adder and incrementer. Using these 4 plus whatever we have done on project 01, we can, those are the basic building blocks for building this ALU, right. So, with this we complete module 2. Any doubts you have, please put on the forum and we can basically take it forward from there. Thank you.